All right, we're going to continue with our warm-up example, and we're going to try and get into a little bit more detail about how you would generally find this formula for the derivative function. So far, we started with function f of x equals 4x minus x squared, and we've basically got a conjecture that f prime of a is 4 minus 2a. We got here just by crunching through the limit definition multiple times and looking for a pattern in the values of the derivative. Now I'd like to work on finding a way to do this that's a little bit more efficient and a little bit more reliable. Sometimes the patterns we see in the values of derivative are a lot less obvious, and it can get really challenging to just guess at a formula that fits the pattern. So to do this, we really need to go back to the definition of the derivative. What I want to find is this f prime of a, which according to the definition of the derivative is going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. And we've been using this by selecting a specific a value and then crunching through the simplification of the difference quotient. But if we want a more general formula where we haven't pre-selected the x value, we can get that just by not plugging in a value for a. We leave the a in there. So for this formula, we'll get the limit as h goes to, hold on, I see it, h goes to 0 of 4 times a plus h minus a plus h squared, and then we need to do minus f of a, which would be 4a minus a squared, all over h. All right, so we have to go one more time through this simplification. If you stopped and did a couple of these, you're probably tired of doing this really similar work, but this is going to show us how to get that general answer without the pattern recognition piece. So we'll distribute the 4 through 4a plus 4h. A plus h squared, if we multiply that by itself, we'll get a squared plus 2ah's plus an h squared. Remember to distribute that minus sign, really important. So it's minus a squared minus 2ah minus h squared. And then we also need to be very careful about distributing the negative sign through the f of a. So we will end up with minus 4a plus a squared, and that's all over h. And now nice things start to happen. I see 4a minus 4a, that adds up to 0, so I can cross it out. I see a squared, negative a squared plus a squared, which adds up to 0, so I can cross it out. And everything that's left over includes an h, so I'm now ready to factor that h out, and I'll be left with a 4 minus 2a minus h. When I cancel the h out, I'm finally ready to let h go to 0, and when h goes to 0, all I'm left with is 4 minus 2a. So what I've just calculated is that f prime of a is equal to 4 minus 2a, and I'm feeling delighted because that's exactly what we conjectured on the first page. That's what our pattern recognition nudged us towards, and we've just verified that if we let a just be a, we don't select a value for x, this formula will allow you to input an x value and output the derivative or the slope of the tangent line. So if we ever wanted to be able to find more than one value of the derivative, this would give us a formula that would allow us to calculate any of those. Now, truthfully, there's no reason for us to call our x value something other than x. Here we're calling it a. But in the original function, we call our x value x, and in the derivative, we can do that as well. Really, all that's going on here is since we first built up the idea of the derivative at a specific point, we use that a to really emphasize the idea of we're being particular and picking a specific a value instead of allowing any old x value. So it's a variable representing something that we want to be constant versus a variable that really can be any value that can vary. But now we're saying use whatever x value you want and plug it into the formula to get the slope of your tangent line. That's what x already does. So we don't need to give it a new name. The fact that we were using a is really arbitrary and kind of unnecessary. So we can just keep it as x, and that's what we'll do for now on. So really, we would just say that f prime of x is equal to 4 minus 2x is the formula for the derivative. Here we'd be plugging in x values just as we would in the original function. Those have the exact same meaning, and outputting slopes of tangent lines. All right, let's go ahead and sneak in a definition to formalize what we've just said. So now, for any value of x, so for any x in the domain of the original function, in the domain of f, we define the derivative function, which can be written f prime of x, or the derivative of f of x, or if we're saying y equals f of x, we could just use dy dx. All of these notations are good. Note that the d over dx is the part that means derivative. So when we write dy dx, we're really saying the derivative of y with respect to x. So we're taking the derivative of function y, and we treat this dy dx type notation a little bit like fractions. So we just move the y up into the numerator. All right, so we define it as the limit as h approaches 0 of f of x plus h minus f of x all over h. So you will crunch through your difference quotient work. You will evaluate the limit as h approaches 0, and what you end up with will be the derivative of f, the derivative function. All right, let's wrap this up by looking at the graphical meaning of what we've been doing. We'll look at this a lot visually going forward, and in particular, we're going to do more in this section, and it can be a really challenging part of this section. So let's think about what we just did. We started with our function, f of x equals 4x minus x squared, and that's this one right here. And we've created a new function where if we input an x value, we get the slope of the tangent line at that x value. So for example, if x equals 0, we're at the point 0, 0, we can draw a tangent line, and we know that the slope has to be 4. We can get that out of the formula. You can look back at the first page. So there's our tangent line. Slope is 4. What this means is that on the graph of our derivative function, when x equals 0, so x has the exact same meaning, your output is 4. So the slope of the tangent line becomes your y value. If we look at the function when x equals 1, we get a tangent line with a slope of 2. The value of our derivative is 2. So when we move over to our f prime graph, when x equals 1, our y value is 2. Our slope becomes our y value. When we look at x equals 2, our tangent line has a slope of 0. So the value of f prime is 0. The slope is 0 becomes the y value of f prime, which is 0. If we look at x equals 3, we get a slope of negative 2, which means the derivative goes through 3, negative 2. And if if the x value is 4, the slope is negative 4, which means the derivative goes through 4, negative 4. And you can see that same pattern we recognized up above. We've got a constant slope going on here. This is a linear function, and we already have its equation. It's 4 minus 2x. So if we look at this a bit more holistically, we can work our way along the graph of f and talk about what the slopes are doing, and we should be able to see what's happening on the graph of f prime reflecting that. So starting from the far left, we have fairly steep positive slopes over here if we visualize our tangent line. As we work our way along, those are getting a little bit smaller. Our tangent lines are less steep, and they continue to do that until right at x equals 2, we have a slope of 0. And then after that, our slopes become a little bit negative, and then more negative, and more negative, and more negative. And remember, I'm talking slopes, not y values. It's really hard to train your brain to think that way at first. So I started with big positive values. They got smaller and smaller. At 2, they became 0. They switched to negative, got more and more negative. When I move to my derivative graph, I should be able to say that about y values. My y values start big positive. They're getting smaller and smaller. At 2, they become 0. They switch to being negative and then continue to get more and more negative. So one of our goals will be able to look at a graph of a function and get a pretty good idea of what the graph of its derivative will look like. And that's a challenging one. So we'll continue to work on this both algebraically and graphically. But I think that's pretty good for our intro. Thanks for watching.